Now, before we start, I'd like to introduce a very special guest.
Welcome back to Cartoon Physics. Today, we're looking at Antman. The original Antman was a scientist turned superhero in the Silver Age of comic books. He used his invention, the Pym particle, to shrink down to the size of an ant. The 2015 MCU movie explains the Pym particle like this.
I immediately started researching a particle that could change the distance between atoms while increasing density and strength.
Beyond the suspension of disbelief, what he's talking about is the conservation of mass, meaning that Ant-Man's full-sized strength can be concentrated down to the size of a bullet. The movie takes artistic liberties to let him do things like running along the top of a gun that someone's holding and ride an ant without crushing it. And in the 2018 sequel, Antman and the Wasp, he uses the inverse Pym particle to become Giant Man. In the scene at the San Francisco Bay, Giant Man catches up with the bad guy who had stolen their shrunken lab, which apparently weighs as much as a briefcase.
That doesn't belong to you!
No! No! No!
You're embarrassing yourself now. Come on.
This leads to the question, what would happen if Giant Man retained his original mass? Spoiler alert, he'd basically be a giant balloon. Quora user Thomas Vizik gives us a good estimate that Giant Man's size is about 64 meters. And Ant-Man's original size is listed on Marvel.com. We'll also use some values like the density of air and the density of seawater, which are readily available online. So, in this trilogy of lessons, we'll look at Ant-Man becoming Giant Man, who should be renamed Balloon Man. We'll calculate his initial acceleration upwards, his terminal velocity, and then his maximum height. Let's get to it. Along with Ant-Man's given heights, we're going to calculate the ratio of those heights. And note, this is only along one dimension. We also have rho sub I, which is a value for the density of the human body. This problem is largely about density and volume. Here, we're using the given values to calculate his initial volume. Then we calculate his giant volume. This is where we use the ratio of heights. Note that we cube this ratio now because he's changing in length, width, and height. Then we'll draw a free body diagram and calculate the forces. Note that 2/3 of his body are above the water and 1/3 is below. This is important because buoyant forces are based on the volume and the density of the fluid they displace. We also have the force due to gravity, which is m times g. We'll refine our equation for the buoyant force. Note that 1/3 of the volume is water and 2/3 is air, so we'll use those densities. We can plug in values now. The density of seawater and the density of air are values you can find online. The density expression is multiplied by volume and then multiplied by gravity, 9.81 meters per second squared. This comes out to be about 14 meganewtons. Back to our free body diagram, we'll sum the forces in the y direction. We have 14 meganewtons going up and 890 going down. 14 meganewtons is way more than 890 newtons, so when we sum these, we still end up with about 14 meganewtons. Then we have F equals ma. We'll rearrange this to solve for acceleration, plug in our values. This comes out to about 154,000 meters per second squared, which means Balloon Man experiences over 15,000 Gs when he takes off. And that's how we can calculate Ant-Man's initial acceleration. In the next episodes, we'll calculate Ant-Man's terminal velocity and then his max height. Thanks for watching Cartoon Physics.